Hello, my name is Christopher Clark, and I'm going to be presenting Molmo2, a new vision language model from AI2. And this is joint work with many colleagues from AI2 and the University of Washington. So, what can this model do? Well, there's a big focus on video understanding. So, this includes video grounding capabilities like being able to track an object across many frames or track multiple objects across many frames. It includes pointing and counting to objects or actions in the video. It includes familiar capabilities like captioning videos or answering complicated questions about videos. Some other highlights of Momo2 that make it stand out from other VLMs are that it's fully open. So we release not just the weights, but also all the training data and the training code so people can directly build off our work. It's also non-distilled, so we don't train on output derived from other closed source VLMs, which is to make the data pipeline more transparent and open than if we had this kind of circular dependency of having a black box VLM inside our training pipeline. And then there's a big focus on grounding, similar to the old MOMA model, but here we're grounding in both space and time for videos. So, of course, to do this, we built a lot of data. We have 9 new data sets. I won't have time to go into the details of all of them. They all have their own data pipelines. There is a lot for video, also for some for multi-image. So we also are trying to improve multi-image support in this model. It's a mix of synthetic and human annotated data. I'll mention a couple in a bit more detail. So this dense captioning data set has 1 to 3 minute long videos accompanied by these really long, dense captions. And to build this, we had human annotators record clips describing individual clips of the video. So humans got a 5 to 15-second clip of the video and then would verbally record a description of that clip. And then they'd go through the whole video clip by clip. Then we had Momo caption frames, and then we combine these together to the full caption. And this tends to work well because the Momo frame captions are very detailed about visual details, so about the background and what objects look like. And the human annotators we find tend to naturally focus on actions and events and what's happening. So you can combine those together to get really complete captions. There's also a lot of video pointing data for objects, actions, referring expressions. So here we have annotators directly look through the frames of the video and click to annotate the data. There are many other data sets. Again, I won't go into all the detail. You can see the paper. And then the model itself is going to be pretty familiar with a pre-trained vision encoder and language model that are connected together. To do video, we sample frames from the video at a uniform FPS. The FPS is variable depending on how long the video is. And then we just input those frames into the model as we would an image. We did add bidirectional attention between image tokens, which we find boosts performance. To train this thing, we pre-train on image captioning and image pointing. We found adding image pointing to the pre-training helped quite a bit in stabilizing the pointing and grounding performance. And then we do SFT on this huge mix of data, both the new data sets and a bunch of academic data sets that we collected. Some new tricks here are tuning the weight, the token weight, not just the data set mixing rate, some of the data sets with really long output responses to better balance them with the data sets that have short responses. And also some efficiency tricks with packing and message trees where we can get many, many examples kind of compactly represented into one sequence. So our final mixture had, on average, 16 examples for a max length sequence in the training data. Again, I'll leave details to the paper. So we evaluate this on short video. So on short video, this is an average of 6 short video benchmarks. And here we're ahead of other open source models and even open weight models, but then a bit behind some of the best proprietary models. On long video, we're ahead of most open weight models, but behind Eagle 2.5, which had a big long video focus. And then here we see proprietary models are well ahead. We evaluated counting. So for Molmo2, counting is a grounding task, so the model points at every object it's trying to count. And here we're very strong, competitive with proprietary models and ahead of other open models. And then on tracking, Molmo2 is state of the art. And very few VLMs really support video tracking, even though we think it's a pretty fundamental grounding capability for video. Many other results in the paper on images and ELO and image pointing, but I won't talk about them here. And then thank you. So again, all the code and data is available. There's a lot of ongoing work as well at AI2, both adapting it for things like robotics or for agents, and also active ongoing work on building the next generation of VLMs with a focus on grounding or reasoning or spatial intelligence. Thank you.